concept of NA and limit of resolution. Okay, so you have this picture on your slide that you can consider your object. Okay, your object is now you can consider as a diffraction grading. Does it make sense? You have transformed your idea of your object as a multitude of grading, and you shine your light. Okay, and now you can consider this interaction of your light with your object as a diffraction grading phenomenon. So what that means, now you have this grading spot, and you have this aperture size or spacing of the grading as D, and you have now the first diffraction. I'm not talking about zeroth, the first diffraction. And what that means, you have now angle theta J, let's say jth grading, jth diffraction. Then now you can also remember from your previous, maybe high school, so you can have this angle as theta J as well. Okay. And now we have a objective lens or lens. So let's make a nice central line. And as I say, back focal plane of your object is a dot. And let's try your first order diffraction as this line. And of course that passes through, and because it's a lens, it will form an image on your image plane. Let's say this is an image plane. Okay, as Hyun just said, to form an image, you need at least not just one. More than one of diffraction has to pass through the system so that you can make an interference. So this is a theta 1. So you at least need one more, like I assume, like this one. So that is theta J. And that passes through so that it can contribute to focusing an image. And then, of course, diffraction happens all the time. So you can have many diffractions, okay? And another thing to point out is this media has refractive index N index. What that means, you can consider the wavelength lambda is effectively shrunken by N. So that's it. So instead of lambda, you should use lambda over N if the media is filled with N. So that's what I want to make sure you understand that part. Okay, so let's go back to grading equation. Okay, that's you remember this tiny triangle, and that's optical path differences. So that optical path difference is D times sine theta J. Okay, and remember from the grading equation that optical path should be multiple of your wavelength to make a constructive interference or diffraction. So that must be J times usually lambda, but I'm now putting lambda over N. Why? Because if you fill this one with the media of N, it's effectively shrunken your wavelength by that. Okay. The important aspect here is, your theta J here, theta J has to be passed through this object length. Otherwise, it's go outside, you can't form any information. So as theta J must be smaller than theta max. And theta max is half the angle. Okay. What does that mean? From the one, you can find out J has to be smaller than D times sine theta now max over lambda over n. Does it make sense to everyone? Okay. Yeah. From the grading to form an image, you have to match these ones. So J is just an integer number. You need to have 1, 2, 3, at least integer number, which makes sure that this parameter. And that is, let's make a little bit of a readjustment. Lambda over, let's bring the sine theta down. So there's n sine theta max. You see, there's some familiar formula out here. So why don't we define that part? Hey, this is very kind of important parameter you can find. And here D is just the size of the feature. So now we can define D over lambda over NA. So what does this mean? So let me go back. D is in fact the grading spacing, but it's actually smallest feature size. Small list feature size of your object. Okay, so how can you interpret this? Okay, so to form an image, what you find is the integer j has to be smaller than d over lambda over na. What does this mean? Thus, your resolution is determined by the how many diffractions you actually suck through your optical system, by the maximum possible number of j. That determines the information or resolution, or this is the ratio. I mean, this one, the ratio of D. I say D is a minimum feature size of an object, right? And the ratio of D and lambda over NA, where we define NA as n times sine theta max. So you want to increase the number of J, means the ratio between your smallest feature size divided by this content. And so this one, the smaller the lambda over NA, you have more number of J's possible and you have a better resolution. So thus, what matters is actually this parameter, how small this parameter is, how many diffraction information you are passing through, how high your resolution is. Thus, the limit of your resolution. You don't have to write it down because I'm going to send it to you, okay? Is proportional to the parameter of lambda over NA. So in the end, what does this mean? Let me go back to just stop sharing. Let me share the screen again. So this one, and actually I think I can now reopen this. One slide. I just wrote it here, what I wrote. So derivation of the concept of NA and the limit of resolution. So let me go back. So we have an object, and in the end, the diffraction, the number of diffracted light which pass through this optical system makes your image. And the higher the angle, you see, the higher the angle is related to the smaller feature size. And what we found is the number of J is limited by the maximum angle, and J is an integer, and J has to be smaller or the same as Indian D over this parameter. But the D is of course the actual object, minimum feature size of an object, and the J, the more number of J's we need to pass through, then the smaller this bottom or denominator determines that. So this, we realize lambda over NA becomes the most important parameter. If this one's smaller, you will have a better information or better resolution. So to make this one small, you would probably use a smaller wavelength that makes sense, and or higher NA. So this is how we guess Abe reached it to define numerical aperture, and this is a key aspect of our resolution. Okay, so with that, I think what happens is, hey, you have an objective lens. Remember, you have 4F system tube lens, you have point source, CCD. In fact, when I was like you graduate students, I just took pictures. This is what my image on my CCD. So it like broadened, and that actually looks like airy disk. So half of this is in fact 0.61 lambda over NA. You see, this is now defined as a Rayleigh criterion. Okay. So this is the radius of the airy disk, and that's what we define from central lobe to first zero side lobe. And that we define as a Rayleigh resolution, and we define that as a point spread function. And let me ask you a quick question. What would be the images of 100, 10, 50, 100 nanometer object when we are using a typical microscope? Sadaf, let's say our Rayleigh criterion, the resolution comes out as a 300 nanometer, and now you put this 10, 50, 100 nanometer object. What will be your image size? Can you guess? I mean, you can just say what you think. Excuse me, I can't hear you.
I don't know.
Okay, Suhyun. You have a PSF of size of 300 nanometer PSF. With that system, what will be your image for this tiny object? Okay, Brahanu?
Yes, Professor.
Yeah, so you have a point spread function or resolution of 300 nanometer imaging system. With that system, you take picture of 10 nanometer nano like quantum dot. What will be the size of your image? Yeah, I'm not asking you a very difficult. You look at that point spread function. If you take an image of point, you will get 300 nanometer image, like that's airy disk. Okay. When I say point, that probably means 1 nanometer or below. Now you take pictures of 10 nanometer. It is smaller than this. You will still have blurring of this size. Zhang Myung. What will be the
That's
image size of your 100 nanometer object you take picture? What will be your image size?
still more than 300.
You mean smaller than 300? Okay, or what you say just is all wrong. With the resolution of 300 nanometer system, even if you are taking image of a smaller object than 300 nanometer, you always have 300 nanometer or bigger. That's why your resolution is that one and limited. Even point will become 300 nanometer. If you take image of smaller than your resolution, you will just get out as point spread function. Okay, so this is shocking. I mean, this is the concept of the resolution and point spread function. And hopefully you can actually consider that. And I think that the rest I already discussed with you about radiate criterion. In practice, we use full width at half maximum as a practical measurement of your optical system. You see, this PSF is when you are taking 1 nanometer image, you still have PSF coming up. Okay, that's the fundamental limit of diffraction limit, and that's why I emphasized why we define numerical aperture, and that's the limitation of optical system. Actually, it's not only optical. In fact, other kind of wave-based imaging system is just the same. And I wrote down point spread function and resolution. Let me see. How many of you have heard impulse response function in your previous classes for electrical engineering or signal processing? Raise your hands. How many of you have heard impulse response? Oh, okay. Sadaf, no? Okay, yeah. In electrical engineering, you have a system, you want to measurement system, you send out pump impulse. Mathematically is a direct delta function coming in, and you will have kind of boom, and then you have a tail, like RLC circuit tail, and that size determines the temporal resolution of your measurement system. It's exactly the same concept, just 2D spatial aspects and not temporal domain. So point spread function we call sometimes impulse response, because a geometric point is represented by delta function, and it always spreads out. And the amount of spreading is related to your diffraction, and that's relevant to your wavelength, annual aperture size, or now we consider it numerical aperture. Okay, so this is a 3D PSF. We talk about just 2D laterally, but actually 3D is axial as well. So Z-axis, it looks quite weird shape, and usually it's a lumpy ball shape. So you have to know that axially we have always suffering our resolution. And the reason is radial versus axial are a little different fundamentally. So you have an object, you see this big and small object, and this is PSF. My question previously is the same. If you have a tiny one, like really tiny object, your image is still the same as PSF. Of course, you have a much bigger one. What your image processing is the object convolution of your point spread function, so it will be blurred. But the important thing is, even tinier than this point, would you take an image, you'll always get the PSF. That's why you cannot make it even smaller than this. That's a resolution limit. So I put this on 3D, and this is an example of the black one is the real data. You won't find out the nice Gaussian curve in reality unless you have a very much of a signal. But this is the reality. Sometimes you have a Gaussian fitting for that. So let me summarize. You know, I know this is not easy. I have to admit that it took me more than 10 years to thoroughly understand this concept. So it's like too much for you to understand it in 10 minutes, an hour, but I basically summarize what I describe is diffraction. It's a fundamental process of image formation. You can consider your sample as a summation of gradings, but think about your sample, the fine feature will have a narrower grading compared to your wavelength. Narrower grading means when it diffract, it will bend the bend more because there's more diffraction. Your smaller feature size, when interact with the light, it will bend more. To capture that information, you need a bigger lens to capture that diffracted light. That's why bigger lens or bigger numerical aperture will be able to capture smaller feature, which is a smaller grading period. And so Abe reached to the conclusion of, hey, diffraction is a key phenomenon when we form an image. So when we consider this, we define lambda over n sine theta is the key parameter to extract this information of the feature of the sample. So n sine theta is the bigger this one, you will have a better resolution. And in fact, your resolution formula is lambda over NA. Actually, I want to go back just one more slide. Hey, your resolution formula is actually lambda over NA. And you even memorize this one, 0.61 lambda over NA so many times. Or just say about half of the wavelength over NA. So the bigger NA, the smaller of this, the smaller of this D or high resolution. So that's the key aspect of what you take out from this today's lecture. And in the end, resolution is defined by your point spread function. And we just use a Rayleigh criterion of the resolution. And we define concept of numerical aperture. It's not just something you have to memorize. It's from this reasoning that this n times sine have the maximum cone angle is determining the resolution. And the end result is point spread function. Here, I want to stop and I